somewhere out there, so far away that the distance can't be written in a way your brain will accept, there is a planet with oceans shaped like ours, continents drifting in almost the same pattern, and a species standing on its surface right now looking up at a sky and asking whether they're alone in the universe. And the strange part isn't that this might be true. The strange part is that if a few basic things we already believe about the universe are correct, it isn't just possible. It's required, not likely, not plausible. Required the way it's required that if you flip a coin enough times, you eventually get a run of 10 heads in a row. Before we get into why, if you're the kind of person who likes having their sense of reality gently rearranged, go ahead and subscribe now, because that's basically the whole job of this channel. Okay, let's start with the assumption almost everyone walks around with, whether they've ever said it out loud or not. The assumption is that Earth is one of one. That somewhere in the vastness of space there might be other planets, maybe even other life, but that our specific Earth, this exact arrangement of oceans and mountains and cities and the specific way the clouds looked this morning, is a one-time event. Unique, unrepeated, the only copy that will ever exist. It feels obvious. It feels like the kind of thing you don't even need to question. But here's the uncomfortable truth about that assumption. It was never actually based on evidence. It was based on the fact that we've never seen another Earth, and human beings have a very old habit of treating "I haven't seen it" as if it means it isn't there. We did this with germs before microscopes. We did it with continents on the far side of oceans before ships could cross them. We did it with galaxies beyond our own before telescopes were powerful enough to resolve them. There's an old story worth remembering here. Back in the late 1500s, a monk named Giordano Bruno stood in front of some of the most educated people in Europe and said something that sounded, at the time, like complete lunacy. He said the sun was just one star among countless others, that those other stars likely had their own planets circling them, and that the universe was probably infinite in extent, with no special center and no special edge. He had no telescope, he had no way to prove any of it. He was working purely from the logical extension of an idea, the same kind of reasoning we're using tonight, and for saying it out loud in public and refusing to take it back, he was eventually burned at the stake in Rome in the year 1600. It took astronomers another few centuries and considerably better instruments to confirm that he was, broadly speaking, right. The Sun is one star among hundreds of billions in our galaxy alone. Other stars do have planets. We've now directly detected thousands of them. And the universe, as we're about to see, really does look like it stretches out far beyond anything we can see the edge of. Every single time human beings have assumed our specific corner of the universe was uniquely alone, a one-of-one exception to how everything else seems to work, the universe has eventually shown us the opposite. Our sun isn't special. Our galaxy isn't special. The specific corner of space we happen to occupy isn't special. And there's a very good chance we're about to learn that even Earth itself isn't the one-time exception we've always assumed it to be. To be clear from the outset, nothing in tonight's video claims this has been observed, photographed, or confirmed in any direct way. What we can say, based on what we know about the geometry of space and the behavior of matter at the quantum level, is that certain conclusions follow almost automatically once you accept a small number of well-tested starting points. Where the evidence is solid, I'll tell you plainly that it's solid. Where we're extending that evidence into territory no instrument could ever directly check, I'll flag that too, because that distinction is the entire difference between a genuine scientific implication and a guess dressed up to sound like one. For most of the early 1900s, the leading astronomers of the day genuinely believed the Milky Way was the entire universe. Full stop. They looked up at faint, fuzzy smudges of light through their telescopes, called spiral nebulae at the time, and assumed those smudges were simply clouds of gas swirling somewhere inside our own galaxy. Nothing more exotic than that. Then, in 1923, an astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California with what was then the largest telescope on Earth, identified a specific type of star inside one of those smudges, a star called a Cepheid variable, whose brightness pulses in a way so regular and predictable that astronomers can use it like a cosmic yardstick to calculate exact distances. When Hubble ran the math on the distance to that particular star, the number that came back was so large it meant the star, and the fuzzy smudge of light it belonged to couldn't possibly be inside the Milky Way at all. It had to be an entirely separate galaxy, sitting millions of light years beyond the edge of our own. Overnight, the known universe didn't just get a little bigger. It got unimaginably larger, and it turned out to be filled not with one galaxy, but with what we now know to be roughly 2 trillion of them, each one containing on average around 100 billion stars of its own. Every single time human beings have drawn a line around what exists and confidently said, "This is everything, this is all there is," reality has eventually erased that line and drawn a much, much bigger one further out. There's no reason to think Earth itself gets to be the one exception to a pattern that has held without a single counterexample for the entire history of human astronomy. So let's actually look at the size of the thing we're dealing with, because the size is the whole engine behind this idea. When people picture the universe, they usually picture the observable universe, the part we can actually detect with our telescopes. That part is enormous by any human standard. It's about 93 billion light-years across. To get a feel for how big that number really is, remember that a single light-year, the distance light travels in 1 year, is already about 5.9 trillion miles. So 93 billion light-years works out to a number of miles that's a 5 followed by roughly 23 zeros. If you got in a car and drove at highway speed non-stop since the moment the universe began, 13.8 billion years ago, you would have covered something like 1 trillion miles by now. To cross the observable universe at that same speed, you'd need to make that entire lifetime of the universe road trip roughly 550 billion trillion times over. That's not a number anymore. That's just a shape your mind makes when it gives up trying to hold the actual quantity. And here's the part that changes everything. That 93 billion light-year bubble isn't the edge of the universe. It's the edge of what light has had time to reach us from since the Big Bang. It's not a wall, it's a horizon, the same way the horizon on the ocean isn't the edge of the ocean. It's just as far as your eyes can see from where you're standing. Sail further and the horizon moves with you, revealing more ocean that was there the entire time. Space works the same way, except instead of a boat, you'd need something that doesn't exist yet, and instead of water, you'd be sailing through the fabric of reality itself. So the real question isn't how big is the universe we can see, it's how big is the universe, period, including the parts light hasn't had time to reach us from yet. And that question turns out to hinge on something you wouldn't expect: geometry. Specifically, the geometry of space itself. This isn't a metaphor. Space, the actual three-dimensional fabric that everything exists inside of, can be curved, the same way the surface of a sphere is curved or the surface of a saddle is curved, and we can actually measure which kind of curve our universe has. Here's how. If you draw a triangle on a flat sheet of paper, the three angles always add up to exactly 180 degrees, every time. That's basic geometry you probably learned in school. But if you draw a triangle on the surface of the Earth, using the shortest possible paths between 3 points the way an airplane would fly them, the angles add up to more than 180 degrees because the surface you're drawing on is curved outward, like the outside of a ball. If you drew that same triangle on a saddle-shaped surface curved the opposite way, the angles would add up to less than 180 degrees. 3 possible shapes for space: curved like a ball, curved like a saddle, or flat, where the angles add up to exactly 180, no more, no less. Scientists have actually gone out and measured which one describes our universe using something called the cosmic microwave background, which is the oldest light in existence. A faint glow left over from when the universe was only 380,000 years old, the moment it first became transparent enough for light to travel freely. That ancient light contains tiny, subtle patterns, like a fingerprint pressed into the early universe, and the exact size of those patterns tells us how space itself is curved. Because light traveling from those variations to us gets stretched or squeezed depending on the geometry it passes through. The result, confirmed and refined over years of measurements by a space observatory built specifically to map this ancient light in extraordinary detail, is about as close to flat as measurements get. The most recent precision results, combining that map with independent measurements of how galaxies cluster together across the sky, constrain the universe's curvature to within about 0.4% of exactly zero. Zero curvature. Flat now. I want to be honest with you here, because good science doesn't hide its own uncertainty. A small number of independent reanalyses of that same data have found a slightly different answer, one that hints at a very gentle curve in one particular direction, enough of a difference that some cosmologists have spent the last few years arguing about whether there's an unrecognized measurement error hiding somewhere, or whether we're looking at a genuinely new wrinkle in our best model of the cosmos. That's not a scandal. That's what real science looks like while it's happening. Messy, self-correcting. Argued over by people who'd love nothing more than to be the one who finds the crack in the model. But even the researchers proposing that gentler curve aren't suggesting the universe closes back on itself the way a sphere does, small and finite. They're arguing about a razor-thin deviation from perfect flatness, not a return to the idea of a compact, contained universe you could theoretically travel all the way around. The overwhelming weight of the evidence gathered by multiple independent instruments using multiple independent methods keeps landing in the same place. A universe that is, for all practical purposes, geometrically flat. and that one detail, flat, is the single fact that changes this entire conversation from speculation into something close to mathematical inevitability. If you're new here and you're the kind of person who actually enjoys this feeling, the slightly dizzy feeling of watching a simple assumption get taken apart piece by piece, drop a comment and tell me where in the world you're watching this from tonight. I read every one of them, and it's always strange and wonderful to realize how many different corners of this one Earth are tuning in to a conversation about how many other Earths might exist. Because here's what flat means for the size of everything. If space is flat and it doesn't loop back on itself like the surface of a donut, and there's no strong evidence that it does, then flat space, left alone, doesn't stop. It doesn't curve back around to meet itself the way a sphere does, it just keeps going. Forever, that's not poetic language. That's the literal mathematical consequence of flat geometry extended without a closing loop. A flat universe is either so large that the difference between enormous and truly endless stops mattering for any calculation you could ever perform, or it is, in the strictest sense of the word, infinite. And once you allow for a universe that's infinite, or so close to it that no measurement could ever tell the difference, you've opened a door that mathematics walks through whether you're comfortable with it or not. Here's the walkthrough, and I want to build it slowly because this is the part that actually proves the point, not just gestures at it. Take any region of space the size of our observable universe, the 93 billion light-year bubble we talked about earlier. That region contains a finite number of particles, not infinite. Finite, big beyond comprehension, but countable in principle, the way the grains of sand on every beach on Earth are a genuinely, staggeringly large number, but still a specific, finite number, not an endless one. Every particle in that region can only exist in a limited number of physical states, positions, energies, configurations, because quantum mechanics puts a flaw under how finely you can subdivide reality. You can't have half a state between two allowed quantum states, the same way you can't land on 2.5 when you're counting on your fingers. This means that a region of space the size of our observable universe, despite containing more particles than any number you could casually say out loud, has a finite menu of possible arrangements those particles could be in. Enormous, but finite. Like a slot machine with more combinations than atoms in your body, but still, technically, a specific, countable number of combinations, not an infinite one. Now here's where it gets interesting. If the universe beyond what we can see keeps going, region after region after region, each one the size of our observable universe, and if those far-off regions are built from the same physics, the same particles, the same laws we observe here, because we have zero evidence they'd be any different, then you have an infinite number of regions, each one drawing from that same finite menu of possible arrangements. And this is where a piece of math called the pigeonhole principle comes in, and it's actually beautifully simple once you see it. Imagine you have 10 pigeonholes and 11 pigeons. No matter how you distribute those pigeons, at least one pigeonhole has to contain more than one pigeon. There just aren't enough separate slots to keep everyone alone. Now stretch that idea to its extreme. If you have a finite number of possible slots, meaning a finite number of ways matter can be arranged in a region the size of our observable universe, but an infinite number of regions trying to fill those slots, then not only will some slots repeat, every single slot will repeat, and it will repeat an infinite number of times. There's no way around it mathematically. Given infinite regions and a finite recipe book, every recipe gets used again, and again, and again without end. And one of those infinitely many possible recipes, one specific out of the truly staggering but still finite number of ways matter can be arranged in a region the size of the observable universe, is exactly the arrangement that produces our Earth. Our oceans in this exact configuration, our continents in this exact position. Every mountain range, every coastline, every person who has ever lived arranged in exactly this way down to the atom. If the universe extends far enough and the flatness measurements strongly suggest it does, then that specific recipe isn't a one-time fluke, it's a pattern. And patterns in an infinite space with a finite ingredient list don't happen once. They happen everywhere, endlessly, exactly like every other pattern in that same recipe book. Now, before you get too comfortable with that, let's talk about how far away this other Earth, this letter-perfect physical twin of our planet, would actually have to be. Because this is where the human brain starts to genuinely struggle, and I want to be honest about that instead of glossing over it. The physicist most associated with actually running these numbers, Max Tegmark, working through exactly the kind of calculation we just walked through in a 2003 paper, arrived at two related but distinct figures, and the difference between them matters. Based on the finite number of quantum states a region can occupy, he calculated that the nearest exact copy of a region the size of Earth, meaning just a planet like ours, not the whole surrounding universe, should on average turn up at a distance of around 10 to the power of 10 to the power of 29 meters away. A much bigger ask, an exact duplicate of an entire Hubble volume, meaning everything inside our full 93 billion light-year observable bubble, matching down to the last particle, pushes the expected distance out much further still, to somewhere around 10 to the power of 10 to the power of 118 meters. I need you to sit with how those numbers are constructed, because they aren't just big numbers, they're numbers built by stacking impossibly large numbers on top of each other. 10 to the 15th power is already a quadrillion. 10 to the 100th power, a googol, is already more than the number of atoms in the observable universe. But neither of these figures is 10 to the 100th power. They're 10 raised to the power of 10 raised to the power of 29, and 10 raised to the power of 10 raised to the power of 118. Even that smaller inner exponent, 10 to the 29th, is already far larger than the total number of stars thought to exist in the entire observable universe. This is not a very big number. This is a number specifically engineered by nature's own combinatorics to be as far beyond human intuition as it is possible for a number to be, while still, technically, being a real, finite, calculable distance, not infinite. Finite, reachable, in principle, if you had unlimited time and a way to travel through the specific kind of space that stands between here and there. That distinction matters more than almost anything else in this entire idea. This isn't a hypothetical add-on to physics tacked on for drama. It's what you get according to Tegmark's own published calculation. from taking two things mainstream cosmology already accepts, an extremely flat universe and consistent physical laws throughout it, and following the math to wherever it actually leads, without flinching partway through because the answer got uncomfortable. Try to actually picture it for a second, instead of just letting the numbers wash over you. Somewhere out there, at that first, comparatively closer distance, the one measured in a 10 followed by an exponent of 10 to the 29th, there is very likely a planet the same size as ours, orbiting a star the same size as our Sun. At the same distance, our Earth orbits its own star, because that's what an exact copy of a Hubble-sized patch containing an Earth-like planet would require. Its oceans would hold the same volume of water, arranged into the same continents, because the same physics that shaped plate tectonics here would have shaped it there. Somewhere on that planet, in a city occupying the same coordinates as the one you might be sitting in right now, there could be a version of you made of the same atoms, arranged in the same pattern, with the same childhood memories, the same voice, the same fingerprints, sitting somewhere similar, doing something similar at this exact moment. Because an exact duplicate isn't a rough approximation, it's a total, complete copy down to the last detail, including the fact that they too would probably be watching or listening to something about exactly this idea right now, wondering, as you are, whether it could possibly be true. That's not a coincidence built into the theory for effect. That's what the word duplicate has to mean if you follow the math honestly all the way to the end, instead of stopping partway through, because it starts to feel too strange to be real. I want to pause here and let those numbers breathe for a second, because it's easy to hear a phrase like 10 to the power of 10 to the power of 118 and let it wash past you as noise, the way we do with any number too big to picture. But think about what that larger distance, the one for a full duplicate Hubble volume, would actually contain along the way. Between here and that duplicate patch of universe, you would pass through more galaxies than exist in our entire observable universe, more than once, more than 1 trillion times over, more times than there are atoms in every ocean on our planet combined. And every single one of those galaxies you'd pass would be different from ours, unique, unrepeated, because the duplicate isn't right next door. It's so absurdly far out that you have to burn through almost every other possible arrangement of matter before you circle back around to the one arrangement that happens to match ours exactly. That's not a flaw in the theory. That's exactly what you'd expect from a truly enormous combination lock. The number of possible combinations for even a modest padlock feels large until you actually try them all. Now imagine a lock with a number of possible combinations equal to every particle position in an entire observable universe. You would expect to try an almost unfathomable number of wrong combinations before you got a repeat. And that's precisely what these figures represent. The expected gap, the average spacing between one working combination and the very next place that same combination shows up again in an endless universe. There's a short story written decades ago by the Argentine writer Jorge Luis Borges that captures this idea almost perfectly, even though it wasn't written about physics at all. It describes a library containing every possible book that could ever be written using a fixed set of letters and punctuation. Every combination, every arrangement, stretching on through endless identical hexagonal rooms. Almost every book in that library is complete gibberish, meaningless strings of letters with no pattern at all, because gibberish vastly outnumbers meaning in the space of all possible arrangements. But buried somewhere in that library, because every possible combination exists somewhere within it, there is a book that is a perfect word-for-word account of your entire life, written before you were born. There's another book that's almost identical to it, but gets one detail of your life wrong. There are millions of books that are almost right, and exactly one, somewhere in that unimaginable structure, that's exactly right. The library doesn't care how rare that one correct book is among the noise. Given every possible combination of letters, the correct one has to exist somewhere, precisely because every possible combination leaves no exceptions. Our universe, if it truly extends far enough, works exactly like that library, except instead of books made of letters, it's regions of space made of particles. And instead of a story about your life, one of those regions, unimaginably far from here, happens to contain the exact letter-perfect arrangement of matter that we call Earth. Now, I know what some of you are already thinking, and it's a fair objection, so let's deal with it honestly instead of skating past it. This whole argument rests on two assumptions: that space is genuinely infinite or close enough to it that it doesn't matter, and that the laws of physics stay the same no matter how far you travel. Neither of these is proven beyond all possible doubt. Science doesn't deal in proven beyond all possible doubt, it deals in the best explanation given everything we've measured so far, held provisionally, ready to be revised the moment better evidence shows up. The flatness measurements aren't guesses, they're the product of some of the most precise instruments human beings have ever built, measuring light that's been traveling toward us for 8 billion years. And they keep coming back the same way, flat to within a fraction of a percent. And the assumption that physics works the same way everywhere is called the cosmological principle. And it's not an assumption made out of convenience, it's an assumption that's been tested every single time we've pointed an instrument at a distant galaxy and found the same elements. The same gravitational behavior, the same fundamental constants we measure in our own solar system. Every test we've been able to run says the universe doesn't play favorites with its own rules depending on location. So, while nobody is claiming absolute certainty here, and I want to be honest with you about that instead of overselling it, the two pillars this argument stands on are about as solid as anything in observational cosmology gets. But here's what I find genuinely fascinating, and it's the reason this topic deserves far more than a 5-minute video. The argument we just walked through, flat space, finite recipes, infinite repetition, isn't even the only reason to expect other Earths might exist. It's not even the strongest one, depending on which cosmologist you ask. There's an entirely separate line of physics developed independently for completely different reasons that arrives at a similar conclusion through a totally different door. And this one doesn't require you to travel through ordinary space at all. It requires you to go back, conceptually, to the very first fraction of a second after the Big Bang, to a process called inflation, and to understand why many of the physicists who study it believe that process never actually stopped. Here's the setup. In the earliest moments of the universe, physicists believed there was a period of unimaginably rapid expansion, where space itself stretched out faster than light could have crossed it, doubling in size over and over again in a fraction of a second. This idea, called inflation, was originally proposed to solve some very specific puzzles about why the universe looks the way it does today, why it's so uniform in temperature across regions that shouldn't have had time to talk to each other, and why its geometry came out so close to flat instead of curved in one direction or another. Inflation explains both of those puzzles elegantly, which is part of why it's become such a central pillar of modern cosmology. But when physicists worked out the detailed mechanics of how inflation would actually behave at the quantum level, something strange fell out of the math. Something nobody was specifically looking for. The field that drives inflation, the inflaton, doesn't behave like a smooth, uniform process that starts and stops cleanly everywhere at once. It behaves more like a fluctuating, probabilistic quantity, one that in most regions eventually decays and lets inflation end, allowing normal matter and energy to form, which is what happened in the patch of space that became our observable universe. But in other regions, purely due to the random nature of quantum fluctuations, inflation doesn't end. It keeps going, sometimes even accelerating locally instead of winding down. And in a universe governed by probability rather than certainty, sometimes doesn't mean rarely, it means constantly, somewhere, always. The mathematics predicts that this process, once started, essentially never stops globally, even while individual patches within it are constantly breaking off and ending their own inflation locally, becoming what physicists call pocket universes or bubble universes, each one a fully formed region of space and time with its own Big Bang moment, its own history, and depending on which version of the underlying physics you favor, potentially even its own distinct set of physical constants. Picture it like a pot of water just barely below the boiling point, right at the edge of a phase transition. Most of the water stays liquid, but here and there, at random points, a bubble of steam forms and grows. You've probably actually watched something close to this happen at your own stove, right before a full rolling boil kicks in, when a few isolated bubbles start rising from the bottom of the pot before the rest of the water follows. Some of those early bubbles form, expand a little, and collapse back into the liquid around them, unable to sustain themselves. Others keep growing, breaking the surface, releasing their steam into the air above. Now imagine a version of that pot that's infinite in every direction, where the surrounding liquid keeps replenishing itself faster than it can ever fully convert into steam, so the pot as a whole never actually finishes boiling. Not in 1 billion years. Not ever. New bubbles would keep appearing forever, scattered randomly throughout that endless liquid, an ongoing, ceaseless process of localized transitions happening against a backdrop that itself never fully settles down. That's roughly the picture eternal inflation paints for the universe as a whole, except the liquid is the inflating vacuum of space itself, and every single bubble that successfully forms and grows becomes not a puff of steam, but an entire, fully formed universe, complete with its own stars, its own galaxies, and possibly its own version of a planet like ours. It's worth saying clearly that this isn't an idea physicists reach for casually. The cosmological principle, the assumption that physics behaves the same way everywhere in space, is one of the most heavily tested ideas in all of science, precisely because so much of modern cosmology depends on it being true. Astronomers have pointed instruments at galaxies billions of light years away and measured the exact same spectral fingerprints of hydrogen, helium, and heavier elements that we measure in laboratories here on Earth. The same precise wavelengths of light absorbed and emitted in the same precise patterns, which only make sense if the same laws of quantum mechanics and electromagnetism are governing atoms in those distant galaxies as govern atoms in your own body right now. They've measured the way gravity bends light around massive objects on the far side of the universe and found it bending by exactly the amount general relativity predicts. The same theory that keeps your GPS satellites correctly calibrated in orbit around Earth today. Every test, across every distance we've been able to probe, comes back the same way. The universe doesn't seem to have quiet corners where the rules are different, at least not within the reach of anything we've observed so far. Which means that whatever physics eventually pushes a patch of eternally inflating space into becoming a settled, ordinary universe like the one we live inside. It's reasonable to expect that physics to behave consistently across countless other patches undergoing that same transition elsewhere, each one becoming, in its own right, a complete universe with its own chance, however small, of producing something like Earth all over again. The vast overarching field of inflating space is the pot that never fully boils, and every bubble, every pocket universe, including the one we live inside right now, is a region where a local patch found its way out of that violent inflating state and cooled into something that looks, from the inside, like an ordinary, settled universe, complete with its own galaxies, its own stars, and its own version of a night sky. The physicist most associated with pushing this idea to its logical extreme is Alexander Vilenkin, who along with colleagues worked through the mathematics of what happens if this bubble-forming process really does go on without end in both directions of time. In 2001, working with the physicist Jaume Garriga, Vilenkin published a paper carrying the almost cheerfully blunt title Many Worlds in One, laying out in careful, mathematical detail exactly the kind of argument we've been building tonight, that a sufficiently large or eternally inflating universe doesn't just probably contain repeated copies of Earth. It's essentially guaranteed to. Around the same time, Vilenkin worked with Alan Guth, the physicist who originally proposed inflation back in 1979 to solve a completely different set of puzzles about why the universe looks so uniform, and with the physicist Arvind Bordi to prove something almost unsettling in the opposite direction, that no matter how you construct an eternally inflating model, it cannot have been eternally inflating into the past as well as the future. Something has to have started it. There has to be a beginning somewhere, even in a model built around the idea of endless, ongoing creation. It's a strange, almost humbling detail buried inside a theory otherwise built entirely around limitlessness. The process that may never stop making universes still had to start making them at some point. And physicists remain genuinely divided over what, if anything, came before that starting point, or whether the question even means anything at the deepest levels of physics we currently understand. This model wasn't invented to explain other Earths. Nobody sat down and said, let's build a theory that guarantees infinite planets. It was built to solve very specific, very technical problems about the uniformity and geometry of our own observable universe, and it happened to survive decades of scrutiny from physicists actively trying to poke holes in it. Because it kept making predictions that matched what we actually observe when we look at the sky. The fact that it also implies an endless, ongoing production of new universes, each one potentially large enough in some models to contain its own version of everything our observable universe contains, arrangement for arrangement, atom for atom, wasn't the goal. It was the byproduct. And that's usually how you know a strange idea in physics deserves to be taken seriously rather than dismissed as science fiction dressed up in equations. Not because it sounds exciting, but because it kept showing up, uninvited, as the unavoidable consequence of solving a completely different problem. And here's where it gets even stranger. Because if some versions of this eternal inflation picture are correct, then each of those pocket universes might not just be a repeat of ours elsewhere in some distant patch of ordinary space. Some models suggest each pocket could settle into a different set of fundamental physical constants entirely, a different strength of gravity, a different mass for the electron, a different value for the constants that determine whether atoms, chemistry, and eventually life can even form at all. Change the strength of gravity by even a small amount in one direction, and stars either burn out in a fraction of the time it took life to evolve on Earth, or never ignite at all, leaving nothing but cold clumps of gas drifting in permanent darkness. Change the strength of the force that holds atomic nuclei together by a small amount in the other direction, and hydrogen can't fuse into helium at all, which means no stars, no starlight, no heavier elements ever get cooked into existence, no carbon, no oxygen, no calcium, nothing the periodic table needs to build a planet, let alone a person standing on one. Our own universe seems to sit in a strangely narrow, strangely fortunate range of values on almost every one of these constants. Narrow enough that physicists have spent decades arguing over why that should be the case at all. Eternal inflation, if it's the right picture, offers one possible answer that doesn't require any special explanation or fine-tuning. If endless numbers of pockets form with endless different combinations of these values, then of course we'd find ourselves in one of the rare pockets where the numbers happen to land in the narrow range that allows stars, chemistry, and life. Because we couldn't possibly be having this conversation in any of the countless other pockets where they didn't. Which means most of those countless pocket universes might be nothing like ours, sterile, chaotic, unable to support anything as complex as a planet, let alone a person standing on one wondering about all of this. But most isn't all. In an eternally ongoing process, producing an endless number of these pockets, even an extraordinarily small fraction landing on physics compatible with stars, planets, chemistry, and life still works out to an enormous, uncountable number of universes where something like Earth could form. And among those, following the exact same finite recipe, infinite repetition logic we walked through earlier. But now operating inside each individual pocket that shares our own physics, the same conclusion applies all over again. Somewhere in enough of these compatible pockets, the recipe for Earth gets cooked again. Not once, not rarely. Inevitably, given enough room and enough time, which an eternal process by definition has an endless supply of. I think it's worth being honest about one more thing before we move forward, because I don't want this to feel like I'm just stacking impressive sounding physics on top of itself without acknowledging the obvious problem sitting underneath all of it. We will almost certainly never be able to prove any of this directly. Not with the technology we have now. Not with any technology anyone can currently imagine building. The duplicate Earth from the first argument sits at a distance so vast that even traveling at the speed of light, the fastest anything in the universe is allowed to move, you would never reach it. Not in 1 trillion years. Not in a number of years that would need its own version of the 10 to the 10 to the 29 notation to write down, let alone the far larger figure needed for a full duplicate Hubble volume. The pocket universes from the second argument are, by definition, causally disconnected from our own, meaning no signal, no light, no information of any kind can travel from theirs to ours or ours to theirs, ever, under any circumstance the physics allows. That's an uncomfortable thing to sit with if you want your physics wrapped up with a bow and a clean, testable prediction at the end. Some physicists have pointed to exactly this feature as a serious weakness, arguing that an idea which can never be observed, confirmed, or ruled out by any conceivable experiment starts to drift out of science and into something closer to philosophy wearing science's clothing. That's a fair criticism, and I don't think it should be waved away just because the math is elegant. But here's the counterpoint that keeps most working cosmologists from abandoning the idea entirely. Nobody built inflation or the measurements of flatness to produce this conclusion. Both of those things were developed and confirmed for completely unrelated reasons to explain the uniform temperature of the cosmic microwave background, to explain why the universe's geometry looks the way it does, to solve problems that had nothing to do with duplicate Earths or parallel universes. The existence of infinite repeated regions and the existence of endlessly forming pocket universes aren't separate theories bolted on for effect. They're what falls out automatically once you accept the parts of the model that we can test, and have tested repeatedly with instruments capable of measuring differences of less than 0.5% across distances of billions of light years. You don't get to keep the parts of a theory you like and discard the parts you find inconvenient just because the inconvenient part happens to be unfalsifiable. If the flat geometry is real, and if inflation really happened the way the evidence overwhelmingly suggests it did, then the rest isn't optional extra speculation stapled on afterward. It's the same theory, followed honestly to wherever its own internal logic leads. So now we have two completely independent arguments, developed by different physicists for different reasons using different mathematics, both arriving at strikingly similar conclusions. One says if our own ordinary space just keeps extending outward without limit, which the flatness measurements suggest it does, then Earth's specific arrangement of matter has to repeat somewhere out there, at a distance too large to write down in any meaningful way, but a distance nonetheless, not an abstraction. The other says, even setting that aside entirely, the very process that gave birth to our universe in the first place appears to be one that never actually stopped. One that's still producing new universes right now, each one a fresh roll of the dice, and across an endless number of those rolls, the specific combination that produces something like Earth is going to come up again, and again. And again, an unlimited number of times, in an unlimited number of places we will never be able to see, visit, or prove, but which the mathematics insists must be there. The same way the mathematics insists that if you flip a fair coin forever, you will eventually flip 10,000 heads in a row, not because it's likely on any single attempt, but because forever is long enough to make even the wildest coincidences mandatory rather than optional. And we haven't even gotten to the third mechanism yet, the one that doesn't require you to travel anywhere at all, the one that some physicists argue might be creating new versions of Earth and new versions of you in this very room every single time a single subatomic particle makes a choice about which way to go. This third mechanism doesn't come from cosmology at all. It comes from the deepest, best-tested theory in all of physics, quantum mechanics. And unlike the first two arguments, which push the other Earths so far away that reaching them is physically impossible even in principle, this one suggests something almost the opposite. It suggests that other versions of this exact planet and this exact moment might not be far away in space at all. They might be, in some very real sense, right here, occupying the same location, just along a different thread of reality than the one you happen to be experiencing. Quantum mechanics is, by almost any measure you'd care to use, the most successful physical theory human beings have ever produced. Its predictions have been tested to extraordinary precision, in some cases matching experimental results to more than 10 decimal places, underlying everything from the transistors inside every phone and computer on the planet, to the lasers used in surgery, to the GPS satellites keeping your Maps app pointed in the right direction. Nobody seriously disputes the mathematics. What's disputed, and has been disputed since the theory's earliest days in the 1920s, is what that mathematics is actually describing about the underlying nature of reality once you stop treating it as merely a tool for predicting the outcome of experiments and start asking what it implies about what's really happening in between measurements, when nobody's looking. Here's the puzzle that got physicists into this mess in the first place. Quantum mechanics describes the smallest scales of reality, electrons, photons, atoms, using something called a wave function, a mathematical description that doesn't give you one definite answer about where a particle is or what state it's in, but instead gives you a spread of possibilities, all mathematically real, all coexisting, until something happens that we call measurement. Before you look, an electron passing through a certain kind of experiment behaves as if it's doing two different things at once. This isn't a metaphor for our ignorance, like saying we don't know which one it's doing, so we describe it with probabilities. The mathematics and the experiments confirming that mathematics indicate the particle really is, in some sense, doing both, existing in what's called a superposition, right up until an observation happens. And when that observation happens, something strange occurs. The spread of possibilities collapses down into one single definite outcome. You look, and the electron is in exactly one place, doing exactly one thing. The mathematics, up until that point, predicted a smear of possibilities. The moment you check, reality snaps into a single answer. Here's an example that makes this concrete instead of abstract. Fire a single electron at a barrier with two narrow slits cut into it, with a detector screen behind the barrier to catch where the electron lands. Common sense says the electron, being one solid object, has to go through one slit or the other, like a marble dropped through one of two funnels. But that's not what the experiment shows. Run this experiment over and over, one electron at a time, and the pattern that builds up on the detector screen isn't two simple clumps, one behind each slit, the way marbles would produce. It's an interference pattern, a series of alternating bright and dark bands, the exact kind of pattern you'd expect from two overlapping waves, one passing through each slit and interfering with itself. Each individual electron, somehow, behaves as though it passed through both slits at once and interfered with its own possible paths, even though you only ever detect one single solid electron arriving at one point on the screen. And here's the part that turns this from strange into genuinely unsettling. If you set up a way to actually check which slit each electron goes through, even in principle, even without disturbing the electron in any way you can detect, the interference pattern vanishes completely, and the electrons start behaving exactly like ordinary marbles again, landing in two simple clumps. The simple act of the information about which path being available anywhere in the universe, whether or not a human being ever looks at it, is enough to collapse the wave-like behavior into ordinary, particle-like behavior. This experiment, first performed with light by Thomas Young in 1801 and later repeated with individual electrons, atoms, and even large molecules throughout the 20th century, is often called the most famous experiment in physics precisely because it captures, in its simplest possible form, exactly the puzzle we're wrestling with tonight. For most of the 20th century, the leading explanation for this, called the Copenhagen interpretation, associated with physicists like Niels Bohr, simply accepted this collapse as a fundamental, unexplained feature of reality. The wave function spreads out, and then, upon measurement, it collapses, and physicists mostly agreed not to ask too hard why or how, because the mathematics worked perfectly for predicting experimental outcomes even without answering that deeper question. But a graduate student at Princeton in the 1950s named Hugh Everett found that answer deeply unsatisfying. Working under his advisor, the physicist John Archibald Wheeler, Everett asked a question that sounds almost too simple to be revolutionary. What if the wave function never actually collapses at all? What if instead every possible outcome allowed by the mathematics keeps existing, all at once, and what we experience as the outcome is simply the branch of that expanding structure that we as observers happen to find ourselves inside of? Everett published this idea in 1957 in a paper with the almost deliberately unglamorous title Relative State Formulation of Quantum Mechanics in the journal Reviews of Modern Physics. He didn't call it many worlds. That term came later, popularized in the 1970s by another physicist, Bryce DeWitt, who helped bring Everett's largely ignored idea back into serious discussion more than a decade after it was first published. In Everett's own framing, when a quantum event occurs, when a particle takes one path instead of another, when a radioactive atom decays at one moment instead of another, the universe doesn't pick a single outcome and discard the rest. Instead, the entire universe, including the observer doing the measuring, splits into separate branches, one for each possible outcome. Each branch just as real, just as physical, just as complete as any other, with its own observer inside it fully convinced that their particular outcome was simply what happened, with no memory or awareness of the other branches at all, because those other branches are causally sealed off from theirs the instant the split occurs.
There's a human story tucked inside this piece of physics history that I think is worth telling because it says something about how genuinely radical this idea felt at the time. When Everett traveled to Copenhagen in 1959 at his advisor Wheeler's urging to present his ideas directly to Niels Bohr, one of the towering founding figures of quantum mechanics and the person whose interpretation Everett was quietly trying to replace, the meeting did not go well. आज आकर्षक कंटेंट में बदलें और शेयर करें. Bohr and his colleagues in Copenhagen essentially dismissed the theory outright, reportedly treating it as barely worth serious engagement. Discouraged by that reception and already working a demanding day job at the Pentagon's Weapons Systems Evaluation Group that he'd taken years earlier simply to avoid losing his student draft deferment, Everett quietly walked away from theoretical physics entirely after finishing his doctorate. He spent the rest of his career doing classic content badle or share kare. He spent there founding a private data processing analyst and later founding a private data processing company working on mathematical modeling far removed from the foundations of quantum theory, while the paper that would eventually make him one of the most cited physicists of the 20th century sat almost completely ignored in the scientific literature for well over a decade. He never went back. His idea, meanwhile, kept quietly circulating among a small number of physicists until Bryce DeWitt's championing of it in the 1970s finally brought it back into serious discussion, well after Everett had already built an entirely different life around a field that had rejected him. Everett passed away suddenly in 1982 at only 51 years old. It was his son who found him. That son, Mark Oliver Everett, had almost no idea of his father's scientific legacy while he was alive, and instead grew up to become a musician, eventually fronting a band called Eels, later spending years long after his father's death, learning the full scope of what his father had actually discovered and helping tell that story to a wider audience through documentaries and interviews decades after the fact. It's a strange, quietly moving footnote to one of the boldest ideas in modern physics. The man who proposed that reality is constantly splitting into a practically endless number of branches spent the second half of his life in a branch where almost nobody knew what he'd done before dying without ever really finding out how right the physics community would eventually decide he might have been.
I know how that sounds the first time you hear it, so let's slow down and build it from something more concrete than an abstract particle in a lab. The reason this branching isn't obvious to us in ordinary daily life comes down to a process physicists call decoherence, worked out in detail decades after Everett's original paper, mostly through the work of physicists like Heinz-Dieter Zeh in the 1970s and later refined by Wojciech Jurek. Decoherence explains why we never see large everyday objects like a coffee cup or a person sitting in an obvious quantum superposition, doing two things at once the way a single isolated particle can. The moment a quantum system interacts with its surrounding environment, and everything in the everyday world is constantly interacting with trillions of surrounding particles, air molecules, photons of light, the vibrations of nearby atoms, the different possible outcomes stop being able to interfere with each other in any observable way. They effectively separate into what behave, for all practical purposes, as distinct, non-interacting realities. This isn't a philosophical add-on bolted onto Everett's original idea to make it more palatable. decoherence is itself an experimentally confirmed, heavily tested phenomenon, used routinely in the engineering of technologies like quantum computers, where researchers have to fight incredibly hard, using extreme cold and careful isolation, to delay decoherence long enough to keep a quantum system usefully undecided for even a fraction of a second. The debate among physicists isn't really about whether decoherence happens. Everyone agrees it does, and everyone agrees it explains why the everyday macroscopic world looks stable and definite rather than smeared out and uncertain. The debate is about what decoherence actually means for the branches it produces. Does the universe genuinely split into separate, equally real branches, the way Everett proposed? Or does something else happen? Some additional, still poorly understood process that selects one branch as real and simply discards the rest, the way the Copenhagen interpretation originally assumed, just now dressed up with more mathematical machinery? It's worth knowing, too, that many worlds isn't the only serious alternative to Copenhagen on the table. Some physicists favor an entirely different approach called pilot wave theory, originally developed by Louis de Broglie and later revived by David Bohm, which keeps a single, definite reality at all times by adding a hidden, guiding wave that steers particles along one specific path, never splitting anything at all, at the cost of introducing a different kind of strangeness, where distant particles can instantaneously influence each other in ways that unsettle other physicists just as much as branching universes unsettle everyone else. Physics, as of tonight, doesn't have a settled answer to which of these pictures, if any, describes what's actually happening underneath the equations. And that's an honest, important thing to say clearly rather than gloss over. This is a live, contested topic among people who've spent entire careers studying it. Here's why the many worlds side of that argument has stayed serious and mainstream rather than fading into obscurity the way plenty of speculative physics ideas eventually do. Adding a collapse to quantum mechanics, some mysterious process that reaches in and picks one branch as the real one, requires bolting an entirely new physical process onto the theory. One that has never been directly observed, doesn't appear anywhere in the mathematics of the Schrödinger equation itself, and would need to somehow act instantaneously across space in ways that create serious tension with other well-established physics, including relativity's insistence that nothing, not even information, should be able to influence something instantaneously across a distance. Many worlds, by contrast, doesn't require adding anything at all. It simply takes the mathematics of quantum mechanics exactly as it's written, the same equations used every single day in laboratories, in semiconductor design, in the operation of the device you might be watching this on right now, and refuses to bolt an extra, unobserved collapse process onto it. In that sense, many worlds isn't the wilder of the two options. Depending on how you weigh theoretical simplicity, it might actually be the more conservative one, the interpretation that adds the least to the existing proven equations rather than the interpretation that adds the most. If this picture is correct, and a meaningful portion of the physics community, when surveyed, does take it seriously as at least a leading contender among competing interpretations, then something extraordinary follows almost immediately, whether or not anyone intended it to. Quantum events aren't rare. They aren't confined to specialized laboratory experiments involving single, carefully isolated particles. They're happening constantly, at every scale, everywhere, all the time. Every photon absorbed by a leaf during photosynthesis, every radioactive atom in the rock beneath your feet deciding the exact moment it decays, every random quantum fluctuation influencing the precise firing pattern of a neuron somewhere in your brain. Each of these represents, on the many worlds picture, another branching point, another moment where the universe doesn't choose one path but splits, taking every physically allowed path simultaneously, each one becoming a fully real, separately evolving branch of reality. Given how many quantum interactions occur every single second across an entire planet full of atoms, the branching rate isn't measured in occasional dramatic moments. It's happening at a rate that some physicists have described as effectively continuous. An unfathomable number of splits occurring every fraction of a second, each one spawning its own complete, self-consistent version of everything, including in an enormous number of those branches, a version of Earth almost identical to this one, differing perhaps by nothing more than the exact position of a single atom, or perhaps, given enough branching and enough time, by something as significant as which decisions a person made, which conversations happened differently, which historical events unfolded down a slightly or dramatically different path. Try to hold that image for a second the way you'd hold a photograph up to the light. Every breath you've taken tonight involved trillions of individual molecular collisions, each one, at some deep level, governed by the same quantum uncertainty that makes an electron behave like it's passing through two slits at once. Every photon that struck your retina while you read or listen to a single sentence of this video carried its own quantum history, its own moment of interaction with the atoms in a screen or the air around a speaker, its own point at which, on the many worlds picture, the universe didn't choose one outcome, but produced all of them, branching outward like the countless capillaries running through your own body, each one carrying its own small share of the same original flow. You are not standing at the base of one single towering tree of possibility with one favored trunk called reality. If this picture is correct, you are, and always have been, somewhere out among an almost incomprehensibly vast and still growing canopy, one leaf among a number too large to write down, each leaf every bit as real, every bit as rooted in the same shared trunk of a common history as any other. This is worth sitting with for a moment, because it changes the entire shape of the question we started with tonight. The first two mechanisms we explored, infinite space and eternal inflation, place other Earths at distances so vast, or behind barriers so absolute, that no signal, no light, no information could ever cross the gap between here and there. Many worlds, if it's correct, suggest something almost eerie by comparison. The other Earths aren't necessarily far away at all. They're not elsewhere in space. They're occupying, in some mathematical sense that's genuinely difficult for ordinary human intuition to grasp, a kind of adjacent existence to this one, differing only in which branch of an ever-splitting structure they belong to. A structure that includes this room, this moment, and the version of you sitting in it right now. If you've made it this far, and you're the kind of person who wants to actually sit with a question instead of scrolling past it, I'd genuinely like to know, out of the three mechanisms we've covered tonight, infinite space, eternal inflation, or this branching quantum picture, which one unsettles you the most? Drop it in the comments. I read every single one, And honestly, the answers people give me on questions like this are half the reason I keep making these videos. Now I want to be careful here, because it would be easy to let the excitement of this idea run ahead of what the physics actually supports, and I promised earlier that I'd flag the difference clearly whenever we cross that line. Many worlds is a real, seriously considered interpretation of quantum mechanics, discussed and debated in physics departments and published journals. Not a fringe idea invented for entertainment. But it remains, and likely will remain for the foreseeable future, an interpretation rather than a directly tested, uniquely confirmed fact. Precisely because the different branches, by their very construction, cannot interact with or send information to each other once they've split. That means there's no experiment, even in principle, that could let someone in this branch directly observe or communicate with a branch where a different outcome occurred. Physicists have proposed clever, indirect tests over the decades, ways of looking for subtle interference effects that might hint at the reality of unobserved branches, and quantum computing research, in a strange way, keeps circling back around to questions about whether the strange effectiveness of quantum computers is easier to make sense of if you imagine them performing pieces of a calculation across multiple branches simultaneously. The physicist David Deutsch, who was among the first to formally propose how a quantum computer might actually be built, has argued for decades that the sheer scale of computation a working quantum computer performs is difficult to account for using the resources contained in what we normally think of as a single universe. His reasoning runs roughly like this: a sufficiently large quantum computer can, in principle, perform a calculation involving a number of simultaneous operations so vast that if you tried to physically represent each one using ordinary matter, one particle per operation, you would run out of particles in the entire visible universe before you ran out of operations to represent. If the calculation really is happening somewhere, using something, Deutsch's argument goes, and it demonstrably produces correct, verifiable answers when the computer finishes running, then the most natural explanation, at least in his reading of the mathematics, is that the extra computational work is genuinely being distributed across multiple simultaneously existing branches, cooperating briefly before the answer resolves back into the single branch where you read the result off a screen. Not every physicist accepts this argument, and there are competing ways to describe why quantum computers achieve the speed-ups they do without invoking literal parallel universes at all. But it's a genuine, actively discussed argument, not a fringe curiosity. And it illustrates something important about why this topic refuses to go away quietly. The strange effectiveness of quantum computers is a real, measured, repeatedly confirmed phenomenon, and every serious explanation for why it works, whether or not it invokes many worlds specifically, has to grapple with the same underlying weirdness that Everett was trying to make sense of back in 1957. Decades before anyone had built a working quantum computer to test any of it against. Still, none of this amounts to a definitive test that could confirm many worlds over its competing interpretations. And it's entirely possible that no such test ever will, given how the theory is built. Based on what we currently know, the honest scientific position is that many worlds remains one of several live possibilities, taken seriously by a substantial portion of working physicists, but not yet, and possibly not ever, elevated to the status of settled fact the way say the existence of atoms or the expansion of the universe has been. Let's step back now and put all three of these mechanisms side by side, because each one arrived at a similar destination through a completely different road, and that convergence is, I think, the single most interesting thing about tonight's entire topic. The first argument said, if space just keeps extending outward without limit, which our best measurements of cosmic flatness strongly suggest it does, then the finite number of ways matter can be arranged in any given region means every arrangement, including the one that produces Earth, has to repeat somewhere out there, at a distance so vast it borders on meaningless to a human mind, but which is nonetheless a specific, calculable, finite number, not an abstraction. The second argument said, even setting ordinary space aside entirely, the very process that gave rise to our universe, cosmic inflation, appears by its own internal logic to have likely never fully stopped, continuing to spin off new pocket universes indefinitely, an unlimited number of fresh starting conditions, an unlimited number of chances for something like Earth to form all over again, completely independent of whatever's happening in our own particular pocket. And the third argument said, you don't even need to look elsewhere in space or to other pockets born from inflation to find other versions of Earth. If the deepest mathematics of quantum theory is telling us something true and literal about reality rather than merely providing a convenient tool for calculating probabilities, then other versions of this exact planet and this exact moment might already exist alongside this one, separated not by distance but by branches of a structure our senses were never built to perceive directly. None of these three arguments depends on the other two being true. You could reject many worlds entirely and still be left with the infinite space argument, resting entirely on measurements of cosmic geometry that have nothing to do with quantum interpretation debates. You could remain skeptical about eternal inflation specifically and still find the infinite space argument compelling on its own, since it only requires the universe to be large or infinite, not to have originated through any particular inflationary mechanism. Each argument stands or falls on its own evidence, its own assumptions, its own vulnerabilities to future discovery. Think of it almost like three separate witnesses to the same event, questioned separately in different rooms using different methods of interrogation. None of them aware of what the other two are saying, and yet all three keep independently describing a version of the same underlying story. A cosmologist studying the curvature of ancient light left over from the Big Bang doesn't need to know anything about the mathematics of wave function branching to reach her conclusion about infinite repeated space. A theorist working through the equations of eternal inflation doesn't need the infinite space argument to already be true in order for pocket universes to keep forming somewhere in an ever-inflating background. And a physicist studying decoherence in a laboratory, trying to keep a quantum computer's qubits from losing their delicate superposition for even a few extra microseconds, isn't thinking about cosmic geometry at all. Yet pull back far enough, and all three lines of reasoning arrive in the same neighborhood, a reality built on some form of vast, perhaps limitless repetition, rather than the single, precious, one-time arrangement most of us assume by default. And yet, all three developed by different researchers for different reasons, using entirely different branches of physics, keep landing on some version of the same unsettling conclusion: the universe, examined honestly and followed to the edges of what current physics can say, does not appear to be built for scarcity. It appears to be built for abundance, for repetition, for the same patterns showing up again and again, whether across unimaginable distances of ordinary space, across an endless sequence of newly forming universes, or across branches of reality splitting apart faster than any number could meaningfully describe. So, what does this actually mean for you, sitting here, having just spent this much time thinking about it? I think it's worth being honest that this question can pull people in two very different emotional directions, and both reactions are completely understandable. Some people hear all of this and feel something close to existential vertigo, a sense that if there are infinite or near infinite versions of you out there, making different choices, living different lives, then somehow this particular version, this particular life stops mattering as much. If everything that can happen does happen somewhere, what's the point of trying to make good choices here, in this branch, when some other branch is already covering every alternative anyway? I understand why that reaction shows up, but I think it rests on a quiet misunderstanding of what's actually being claimed. Nothing about this argument suggests your choices in this branch don't matter, or that your specific experiences are somehow less real because a counterpart of you elsewhere is having different ones. The version of you having this exact thought, in this exact room, with this exact history behind it, is not diminished by the existence of other versions any more than one identical twin's life is diminished by the fact that they happen to share their DNA with another equally real, equally independent person living their own separate life. Each branch, each distant duplicate, if it exists, has its own full, complete, self-contained existence, its own consequences, its own value, entirely independent of what's happening in any other branch. You are not competing with your counterparts for the privilege of being the real one. If they exist, they are exactly as real as you are, living exactly as real a life as you are, and neither of you needs the other's non-existence to make your own experience matter. Other people hear this same set of ideas and feel something closer to comfort, even a strange kind of relief. If every path that could be taken is being taken somewhere, then no single choice carries the crushing, irreversible weight it can sometimes feel like it carries in the moment. The road not taken isn't simply lost forever into a void of unrealized possibility. In some branch, according to this way of thinking, it's being walked, right now, by someone who is, in every meaningful sense, you. Think about the specific moment you're in right now, whatever that happens to be. Maybe it's a decision you made years ago that still occasionally aches a little when you think about it. A job you didn't take, a person you didn't call back, a conversation you wish had gone differently. The many worlds picture doesn't erase the reality of the choice you actually made, the one that led to you sitting exactly where you are right now, hearing exactly these words. But it does suggest, if it's correct, that the specific weight we tend to place on irreversible feeling choices, the sense that saying no to one path means that path is gone forever, annihilated, might be built on an assumption about the structure of reality that isn't quite as solid as it feels from the inside. Not because your choice didn't matter here, in this branch, where it clearly did and clearly still does, but because gone forever may simply not be an accurate description of what happens to the paths we don't take, If the deepest mathematics describing reality is telling us something literally true rather than merely useful for calculation. It's a strange kind of comfort, admittedly, one that asks you to find peace in a version of events you'll never get to see, hear from, or confirm. But plenty of people find real comfort in ideas they can't directly verify. Whether that's a belief in an afterlife, a trust that things happen for a reason, or simply the quiet hope that somewhere, some version of a difficult decision worked out better than it did here. What's unusual about tonight's version of that comfort is that it doesn't ask you to take anything on faith alone. It asks you to follow the same equations that already run your phone, your GPS, and the screen you might be watching this on, all the way to their logical end, and to decide for yourself what to do with where they lead. I don't think physics can tell you which of these emotional reactions is the correct one to have, because that's a question about meaning and value, not a question about particle physics or cosmic geometry. What physics can tell you, as honestly as I know how to say it, is that the mathematics describing the smallest scales of reality, when followed without flinching to its logical conclusions, does not rule out either interpretation. It simply describes a universe or a multiverse built on a scale and a structure vastly larger and stranger than the flat single timeline picture most of us carry around by default, largely because that flat picture is the only one our senses evolved to track predators and food and other humans in a single linear stream of time, wherever built to perceive. There's a deeper question lurking underneath everything we've covered tonight. One that none of these three arguments on their own actually answers, and I want to name it clearly rather than pretend we've wrapped up every loose thread. If a duplicate of you exists in some distant patch of infinite space made of the exact same atoms in the exact same arrangement, is that duplicate the same person as you, or a different person who merely happens to be identical? If a branch splits off from this one, carrying a version of you that made a different choice 5 minutes ago, is that branch you, having a different experience, or someone else entirely who simply shares your entire history up until the moment of the split? Philosophers who specialize in questions of personal identity have argued about versions of this puzzle for decades, long before modern physics gave it this particular cosmic flavor, and there isn't a consensus answer, because the puzzle ultimately asks what being the same person even means at the deepest level, whether identity is about continuous physical matter, continuous memory, continuous experience, or something else entirely that we don't yet have a fully satisfying word for. There's an old philosophical puzzle, older than quantum mechanics by more than 2,000 years, that gets at exactly this problem, just wearing a different costume. Imagine a wooden ship that sails for so many decades that every single plank eventually rots and gets replaced, one at a time, board by board, until not one piece of the original wood remains. Is it still the same ship? Most people's intuition says yes, because the replacement happened gradually, plank by plank, with continuity at every step, even though not one atom of the original vessel survives to the end. Now imagine someone collected every one of those discarded original planks as they were removed over the years, and quietly reassembled them in the same arrangement into a second ship somewhere else. Now you have two ships. One has all the original material but none of the continuous history. The other has none of the original material but all of the continuous history. Which one is the real ship? the one that was there at the very beginning. Ancient philosophers didn't reach agreement on this puzzle, and modern philosophers haven't fully resolved it either, precisely because it exposes that sameness was never one single, unified concept to begin with. We use the word same to mean continuity of material sometimes, continuity of pattern and history other times. And we usually don't notice the difference because in ordinary life, those two things almost never come apart. Tonight's physics is exactly the kind of scenario that forces them apart, brutally and completely. A duplicate Earth built from different atoms in a different, unimaginably distant patch of space has all the pattern and none of the shared material history. A branch splitting off from this exact moment has all of the shared material history up until the split, and then an entirely separate, independently continuing pattern afterward. Neither case fits neatly into the ordinary, everyday version of what it means for something, or someone, to be the same. What tonight's physics adds to that ancient philosophical puzzle isn't an answer. It's a much larger, much stranger set of cases to test our intuitions against. Cases involving atoms arranged identically across gulfs of space too vast to measure in any familiar unit, and cases involving branches of reality splitting apart from a shared origin point faster than the human mind can track. The physics gives us the scenarios. It's still up to each of us, and to the philosophers and scientists working at the edges of consciousness research, to figure out what those scenarios actually mean for what a self fundamentally is. I think that's actually the right place to land tonight, not on a tidy answer, because there isn't one yet, but on a genuinely different way of holding the question of what you are. For most of human history, and honestly for most of your own life up until this point, existence has probably felt like a single unbroken line. You were born once, you're living through one continuous sequence of moments, and eventually that line will end, once completely, with nothing on the other side of it that's recognizably you. Tonight doesn't disprove that picture, and I want to be honest about that instead of overselling what we've covered. There's a long tradition in science of exactly this kind of discomfort turning out, eventually, to be worth it. Copernicus made people uncomfortable by moving the Earth away from the center of everything. Darwin made people deeply uncomfortable by tying human origins to the same slow, undirected process that shaped every other living thing on the planet. Every expansion of what we understand the universe to actually contain has, at some point, felt like a loss before it ever felt like a gift, because it always requires giving up a smaller, cozier picture of our own importance in exchange for a true one. Tonight's argument sits squarely in that same tradition, and I think that's worth naming explicitly rather than letting it pass by unremarked. We are not being asked to believe something because it's comforting. We're being asked to follow evidence honestly gathered and repeatedly tested to wherever it leads, even when where it leads unsettles the picture we walked in with. Nobody has captured a photograph of a duplicate Earth. Nobody has recorded a signal crossing from one branch of a splitting wave function into another. Every single argument we've walked through tonight is an extrapolation, a rigorous, mathematically grounded extrapolation built on some of the most heavily tested ideas in modern physics. but an extrapolation nonetheless, reaching into territory that may remain permanently beyond the reach of direct observation. That honesty matters more to me than making tonight's video sound more certain than it actually is. Based on what we can currently measure, what we can say with real confidence is narrower than the full sweep of tonight's argument, but still remarkable in its own right. The universe is, to the best precision our instruments can achieve, geometrically flat. Inflation, in some form, almost certainly happened and left behind exactly the kind of fingerprint we'd expect if it did. Quantum superposition and decoherence are not speculative. They're demonstrated, repeatable laboratory facts confirmed daily in research groups building the next generation of quantum computers. Everything beyond that, the specific distances, the specific mechanisms for duplication, the specific philosophical conclusions about identity and meaning, is what happens when careful physicists, and now, tonight, you and I, follow those confirmed facts to their logical end rather than stopping the moment the implications start to feel uncomfortable. But even held with that honesty, even hedged with every appropriate qualification about what remains unconfirmed and possibly unconfirmable, the picture that emerges is one worth sitting with quietly for a moment before you go back to the rest of your evening. Consider, for a moment, everything that had to hold together just for tonight's conversation to be possible at all. A star had to form in a location stable enough for long enough to let a rocky planet settle into a comfortable orbit around it. That planet needed a moon large enough to stabilize its tilt, plate tectonics active enough to recycle carbon over billions of years, an atmosphere thick enough to hold warmth but thin enough to let starlight through. It needed roughly 4 billion years of uninterrupted, unbroken chemistry, mutation and selection to produce a nervous system complex enough to wonder about any of this in the first place. None of that was guaranteed by the laws of physics alone. And it's worth remembering that we still don't fully understand every step of how that chemistry first crossed over into something we'd recognize as life, let alone something capable of building telescopes, splitting atoms, and writing down the mathematics of its own possible duplicates. Each step was one outcome among a staggering number of ways things could have gone differently, or gone nowhere at all. And yet here you are, made of atoms forged inside stars that lived and died long before the sun ever ignited, sitting at the end of that entire unbroken chain, turning your attention for a few minutes tonight toward the question of whether that same chain might have played out again, elsewhere, endlessly, or split apart into countless branches the instant it began. Whatever the honest answer turns out to be, and whatever new instruments or new mathematics eventually narrow that answer further than tonight's evidence allows, the fact that a pattern this improbable exists even once, and is capable of asking these questions about itself, is already the strangest, most remarkable thing either of us is likely to encounter today. And if it turns out, decades or centuries from now, that some clever experiment finally does find a way to test one small corner of tonight's argument, whether that's a subtle signature of bubble collisions hiding in the cosmic microwave background, or a new kind of quantum experiment that finally settles the question of what decoherence really means, that discovery will belong to a version of this same unbroken chain of curiosity that got you to click on a video like this one in the first place, It will belong to someone standing exactly where you're standing now, on this same improbable planet, asking a version of the same question, carried just a little further down the same long, unlikely line that runs from a collapsing cloud of hydrogen 4.5 billion years ago all the way to this exact sentence. That line, as far as anyone can currently tell, has never run anywhere else before. But if tonight's physics is right about even one of its 3 arguments, it is very unlikely to be the only line of its kind that has ever been drawn. And there is something quietly extraordinary in simply knowing that, whether or not either of us ever finds out for certain. If the universe is flat, and the measurements keep saying it is, if inflation happened the way the evidence overwhelmingly suggests it did, and shows every sign of never having fully stopped, if the deepest mathematics of quantum theory is describing something literally true about reality rather than merely a convenient tool for calculating odds, then this Earth, this specific planet, with its specific oceans and its specific history and the specific thought you're having right now while listening to this sentence, is not a lonely, one-time accident drifting through an empty and indifferent cosmos. It's one instance, one branch, one repetition of a pattern that the universe, if it's as large or as strange as the evidence increasingly suggests, produces again and again and again in more places than any number could honestly describe. That doesn't make this version of Earth or this version of your life matter less. If anything, it reframes what mattering was ever going to mean in a universe this large to begin with. You were never going to be the only place in an infinite or near-infinite cosmos where matter arranged itself into oceans and mountains and a mind capable of looking up and asking these questions in the first place. But you are, undeniably, unshakably, the one experiencing it from exactly where you're sitting right now, in exactly this branch, on exactly this Earth, and no distant duplicate, no forking timeline, no endlessly inflating field of bubble universes changes the fact that this particular thread of existence, the one running through you right now, is real, is happening, and is from the inside. Everything there is.